Okay, so in this section, we're going to talk about complex numbers and polar coordinates. So let's first refresh our memory on what a complex number is. So complex numbers have the form z equals x plus yi, where x and y are real numbers. So the real number x is called the real part. And notice this I here, that's an imaginary number. So the real number y is actually called the imaginary part. So in addition, remember that I squared equals -1. A complex number, z equals x plus yi, can be seen geometrically as the point xy in the xy plane. Label the figure to show that in a complex plane, the horizontal axis is called the real axis, and then the vertical axis is called the imaginary. So this would be the real, this would be the imaginary. So whenever we are plotting these complex numbers, just like before when we did polar coordinates, we had our r and our theta. Now we're going to call the x value, x-axis the real axis, and the y-axis the imaginary axis. Okay, so let's do a couple examples. If we had to graph these complex numbers, we would first create a complex plane. So there's the real, and then this is called the imaginary. My scale is terrible. So if we were looking at this point, you've got the real part is 3, the imaginary part is -2. So that's going 3 on the real, -2 on the imaginary, so that would put us right there. 2 is the real here, 5 is the imaginary, so 2 on the real, 5 up on the imaginary. Here, this 3i, there is no real portion, so that's going to be 0. And then the imaginary part is 3, so 0 is right here, and then up 3. Then the last one, there's no imaginary part. So the real part is -4, the imaginary part is 0. So 1, 2, 3, 4. It's going to put us right there. So a polar representation of the complex number can be written by finding the angle and the radius of the circle drawn to this point. Okay? So we've learned how to do that. So remember that the radius, another way that we can call the radius is by calling it the magnitude. And this is going to come into play next section when we talk about vectors. And the way that you can denote the magnitude is by taking the absolute value of c. Okay, so let's look at this. So if we've got to figure out, using this number, we need to find theta, and we need to find the magnitude, which again is the radius. So first we know that our x value is 3, our y value is -2 from this point. Okay, so I can easily find that magnitude because I know that the magnitude is the same as the radius. Okay, so find that radius. We've got 3 squared plus -2 squared equals r squared. 9 plus 4 equals r squared. So r squared equals 13. So r equals the square root of 13. And that magnitude is going to be the absolute value of that. So it's 13, square root of 13. Okay, now if we're talking about tangent, where to find the angle, we'll use that tangent. So tangent is y over x. So -2 over 3. All right, so take our tan inverse of both sides. And I get about -0.588 radians if I'm doing this in terms of radians. So convert between rectangular and coordinate forms. A complex number can be written as z equals x plus yi. A polar coordinate we know is r theta. So from previous lessons, we know these relationships. We learned that x equals r cosine theta and y equals r sine theta. So we can then do some substitution to find that if I was writing z in terms of x and y, so x is r cosine theta, y I can replace with the r sine theta, and then I still have this I here. So you can see I can actually factor an r out, and I get cosine theta plus I sine theta, where the magnitude is r, the radius. So if we had to complete this table of values, we can totally do that. Looking here, we've got on this first problem, we've got our x value is 3, our y value is -2. We found on the previous slide from that last example that our radius, was the square root of 13, and we found that our theta was about -0.588. Now, if we wanted this to be a positive number, what we could do is, again, remember that if you go on a unit circle, you could go 2 pi, and we'd still end up at the same spot. So I could take that value and add 2 pi to it, and that ends up giving me that theta would be 5.69. So I can rewrite this using the trig form of a complex number, which is z equals, and by the way, you have this formula on your identity sheet, r times the cosine of 5.69 plus I times the sine of 5.69. You just leave it. All right, next one. So here, if we were given it in trig form and we needed to put it in rectangular form, so looking at this, we know that our r is 2 and my theta is 2 pi. So if I looked at this on a unit circle, it's actually really easy to see that x and y coordinate. So if this was a unit circle, our radius is 2, our angle is 2 pi, which is going to put us right here. Radius of 2 puts us there, so you can see that x and y coordinate point is going to be at 2, 0. So if I were to write this, z equals x plus y, yi, so I get z equals just 2. Okay, next one. Our r is 2 and our theta is 2 pi over 3. Okay, so I can figure out, we know that x is r cosine theta. So that's going to give us 2 times the cosine of 2 pi over 3. So 2 times the cosine of 2 pi over 3 is -1/2. So that gives me an r value of -1. We know that our y is r times the sine of theta. So the radius times the sine of 2 pi over 3 gives us 2 times root 3 over 2, which ends up giving us just root 3. So my x value is -1, my y value is root 3, so z equals x plus yi. So in 18th century, there was a Swiss mathematician named Leonhard Euler. It's weird, it looks like it should be Euler, but it's actually called Euler. And he made a connection between exponential functions and the sine and cosine functions involving complex numbers. And this is the formula that he came up with. So that's called Euler's formula. So this allows us to take the definition from the previous page and write it as a progression of complex number in rectangular form to trig form to now polar form. So notice this is polar form because we've got our i's and our thetas. So here's the rectangular form. Here's the trig form. And now here's your polar form. So polar, trig, rectangular. You can kind of see how they all go back and forth. So we're going to be kind of practice rotating between them. All right, so if I had to use Euler's formula to extend the table that we got in example 3. So the first thing that we found in example 3, flip my page over so I have this notes. Okay, so we found that this one had a trig form of the square root of 13 times the cosine of 5.69 plus I times the sine of 5.69. All right, so we know that our r we found was the square root of 13, and my theta is 5.69. So if I had to now write this in a polar form, it's r e to the I theta. Okay? All right. Again, we found that this was 2, or x value was 2, plus 0i, so that gave us a rectangular form of just 2. Our r is 2. Our theta is 2 pi. Or, another case, our theta could be considered 0, because remember that 2 pi and 0 are the same angle. So I could write this as z equals 2 times e to the 0i. And a lot of students want to say, oh, but 0 times anything is just 0, and e to the 0 is 1, so it's just 2. And that's true, but if we wanted to make sure that we were writing it in this polar form, we're not going to simplify this. We're going to leave it just like that. Okay, so the last one we did, we found that we got -1 plus the square root of 3i. Okay, so here we know our radius is 2. Our theta is 2 pi over 3. So if we were writing this in polar form, it'd be z equals the radius, e to the angle, I. Or you could write the I first. We usually end up writing the I second. All right, so now we've got this last one, which we haven't done anything with. So here, this is in polar form, and we need to get it to trig form and then to rectangular form. So we can see here our r is 3, and our angle is pi over 2. So if I were to write this in trig form, this is going to be r, so 3, times the cosine of pi over 2, plus I times the sine of that angle, which is pi over 2. And there we go. And then if we had to write it as an imaginary number, okay, so let's see. So we know that in terms of our imaginaries, first need to figure out our x value and our y value. So x equals r cosine theta. So that's going to give us 3 times the cosine of pi over 2. So that's going to be 3 times 0. So our x value is 0. To find our y value, equals r times the sine of theta. So that's going to be 3 times the sine of pi over 2. So that's just 3. So this is actually just purely an imaginary number, 3i.